Okay, in this last video, I just want to go through 6 basic rules, and these rules can be found on a website called Mech Movies. If you do a search for Mech Movies, you will find a very helpful site, and in the appendix of that site, you will find these 6 rules. I kind of like them. They kind of explain how these diagrams can, again, be easily drawn. The first rule is, and these are some of these rules are things that we've already discussed, but they're kind of good to look at. But the first rule is, it says a concentrated force causes a jump in the shear diagram at that location of the direction of the concentrated force. So you see here in this example that we have a 20 kilonewton force. It jumps down to 20 kilonewtons. It's down at that location. It then sees a 46 kilonewton force. We'll jump up 46 kilonewtons. So that distance is 46. And so it's at a positive 26. It will stay at that till it sees this 40 kilonewton force and jump down to a lower amount of 40 kilonewtons and stay there till it reaches this last part. So this is an easy rule to know. The next rule says the change in the shear force is equal to the area under the distributed load. Okay. So if we look at this, we have a distributed load here of 3 kip-foot. And if we multiply it times our 8, right, it's constant, it will go down to a negative 24. So it's the change in shear force is equal to the area under the distributed load. Then you will see that there's no change in the distributed load or anything. It remains constant during that time. If I do a free body diagram by cutting it here, again we will have a jump of 10 kips, and then there is nothing that happens the remainder of the way. So it makes it really easy to solve these types of problems. The next one is Rule 3, and it says the slope of the shear diagram at any location is equal to the distributed load at that location. So if we look at this, we have our distributed load here of 20 kilonewtons. This slope will again be this negative 20 kilonewtons. Of course, our AY is 52, so it jumps up, and it's going to go down by 20 kilonewtons all the way down. Then it remains constant after it stays there. Then it will jump again due to this 50 kilonewtons and go across. So that's the first 3 rules. So before we get to the last 3 rules, which will pertain to the moment diagram, we want to look at a few little things to know about. And it says to find the bending moment diagram, we will need to find the area under the shear diagram. And it's good to sometimes know what this trapezoidal formula is. So I'm just going to give that to you. And sometimes that is handy to know to be able to find the area under those types of curves. Other things that we want to know is we want to note where the moment conditions are for different types of beams. If we look at a simply supported beam, we see that our moment at a pin location is equal to 0, or a roller location is equal to 0. I never want to see moments there, right? If we look again at this one, which is an overhang beam, the moment here is equal to 0. At the end, the moment is equal to 0. This location where this roller isn't necessarily 0 at that location. And on the last one, we see that our moment here is equal to 0, but not here. And most likely m doesn't equal 0 here either. Okay, let's look at Rule 4. Rule 4 says the change in the moment between any 2 locations on the beam is equal to the area under the shear diagram. So that's all our part of integration. So if I have my shear diagram, which is shown here, I can find my moment diagram by calculating the area under the curve, right? If I calculate the area under the curve, it will start out at a 0 because there's nothing there. The area of this triangle will be a negative 96. This amount is constant, so this will be a linear slope. So this section is linear and will increase by the amount under that section of our shear diagram. Okay, let's stop there and see what the next rule is. The next rule is the slope of the moment diagram is equal to the shear of the force at that beam location. Again, remember this is our dm dx. Our moment slope is equal to our shear. So anywhere along here we will know our moment equation's slope. It starts out at some value of 52 is the slope. It will come out to a 0 at this location, which means that that is a max or min, so it's probably coming up like this. Then it's coming back down with a negative slope. Then it stays constant, and then it changes again with a different constant slope. And the very last rule, it says that concentrated moments cause a jump in the internal bending moment at the point of application. Clockwise external moments cause a jump up in the diagram. So clockwise will cause a jump up. So you see that this one jumps up by 20 kip. So if I kind of erase that, we can kind of see that a little better. If I zoom in, we see that we have a jump in 20 kip foot. So that's due to this jump in this moment up here. Okay, so there's our 6 rules for graphical method for solving for our shear and moment diagrams. These methods and these rules can be used in conjunction with finding our shear and moment as a function of x. It's a good way to check your shear and moment diagrams to see if they actually make sense.